So we're starting chapter 2, which is all about functions. And I want to start talking section 2-1 on functions and function notation. So first, a little bit of vocabulary. A relation. When you have a relation, mathematically, that's just a set of ordered pairs. So here I have a set of ordered pairs. 1, 2, 2, 4, 3, 6, 4, 8. The set of all the first components is called the domain. Those are the x values. So our x values make up our domain. Also, you can think of it as the input value or the independent variable. So the domain for this set would be 1, 2, 3, and 4, because those are all the x values or the input values or the independent variable. The set of all the second components is called the range. Sometimes it's referred to as the output variable or the dependent variable. So the range in this example would be all the y values, 2, 4, 6, and 8. So if you have ordered pairs, it's really easy to pick out the domain and the range. A relation is considered a function if each domain value, which is, think of it like the x value of an ordered pair, if each domain value is paired with a unique range value. So that means that the domain values can't repeat. So for example, this one would be a function because if you look at my x values, I have a 1, a 2, a 3, and a 4. So that means this is a function. An example that wouldn't be a function, if you had something like 1, 2, 1, 4, 3, 5. This is not a function because if you look, we have the x value repeats right here, so that would be not a function. So once you know something's a function, a one-to-one function is a function in which each range value or output value corresponds to exactly one domain value. So this would mean to be one-to-one, the x's can't repeat and neither can the y's. So neither one of them can repeat if it's a one-to-one function. So if you look at the function f of x equals x squared, now this notation is called function notation when you write f of x, and I know you have seen it before. So when you have function notation, it's kind of like having a y. So instead of writing an x and a y, I would write x and f of x. If I were going to graph this, I would have my x-axis and my f of x axes. So it's very much like the y. So if you look at this example, f of x equals x squared, notice it is a function because look at the x values. They don't repeat. But look at the y values. This repeats. So we have in more than one place, we have repeated y values. So even though it is a function, but it's not one-to-one. Okay, so you can check to see if something is if a relation is a function by checking to see if any of the x values repeat, and you can check to see if it's one-to-one to see if you check whether or not the y values repeat, and you can make a decision. So here we're asked to graph the function. Now I'm going to ask the domain and range. We already did that. Graph the function. So I'm going to graph the set of ordered pairs. So remember, this is the origin, 0, 0. In case you've forgotten some of these vocabulary words, I'll remind you. Origin is 0, 0. The point 1, 2, I go to the right one and up 2. Now look how I've scaled my graph. My horizontal axes, I'm counting by ones. My vertical axes, I'm counting by twos. So I've recorded that here to make that clear. So 1, 2 is actually going to be right here. 2, 4 would be right here, because if this is 2, this has to be 4. 3, 6 would be right here, and 4, 8 would be right here. Now there's a temptation when you see the points lining up to want to connect the dots. but this function is just these ordered pairs. So the domain would be 1, 2, 3, and 4. Again, all the x values. The range would be 2, 4, 6, and 8. And that would be the range. Now, this next problem is a little different. You're asked to graph the function y equals 2x minus 1. See, it's okay to say y instead of f of x by making a table of values. Now, when you're asked to do that, you get to pick the values you want to use for x. If it's a line, which this is a linear function, it's enough to just pick 3 points, but I'm going to actually pick 5. I'm going to use -2, -1, 0, 1, and 2. And I'm picking those for my x values. So if I plug a -2 in, I'm going to get 2 times -2 minus 1. So I'm taking the x value and plugging it into my function and getting a y value. So -4 minus 1 is -5. If I plug a -1 in for x, I get 2 times -1 minus 1. So I have -2 minus 1 is -3. If I substitute a 0 in, I get 2 times 0 minus 1. 0 minus 1 is -1. Substitute a 1. 2 times 1 is 2, minus 1 is 1. And then substitute a 2. 2 times 2 is 4, minus 1 is 3. Now I'm going to graph that set of ordered pairs. -2, -5, and I'm going to count by ones this time. So I scale my graph. That's enough. Just you don't have to count all the way up. This is enough just to label one spot there. So -2 corresponds to -5. So I plot that. -1 corresponds to -3. 0 corresponds to -1. 1, 1, and 2, 3. Now notice it looks like a line. Now, whereas I said that in this example you don't connect the dots because they're just ordered pairs, even though they nicely line up, this one I do connect the dots. I'm not going to try though, I'm just going to draw a line like this. But I do connect the dots because I chose these numbers, but I didn't have to choose those numbers. I could have picked a half for one of my x values. I could have picked 2.5 for one of my x values. I could have picked -7 for one of my x values. I could pick any number that I want for x. And then I could have taken that number and plugged it in to find a y value. I just picked easy numbers, but I could have picked anything. And because I could have picked anything, my domain is all real numbers. So be careful, because sometimes students will say the domain and they'll just pick out the numbers they put in their chart. But you picked those numbers and you could have picked any number you wanted. So you have to think about that when you are considering your domain. Your range, by the way, fancy R for all real numbers. Our range also is all real numbers. Now, when you're trying to decide this, notice that I have an arrow on each end of my line. And so this arrow, yes, it's going down, but it's also to the left. So if you move from left to right, all the x values are going to be covered by that line. And if you notice the arrow goes down and then there's another arrow on the other end going up, so all the y values get covered as well. That's the reason why the domain and range are both all real numbers. An easy way to check if a relation is a function is by looking at the graph and applying the vertical line test. So the question is, can you draw a vertical line anywhere on the graph and pass through 2 or more points at the same time? If so, then the relation is not a function. So for my first graph, I'm just going to pick a spot. Now, if I were in class, I could show a line. If I was, well, actually, let's do this. I can do that. Okay, so if I take this line and I move it across here, notice that I'm only going to pass through 1 point at a time. Okay, and because of that, since I only pass through 1 point at a time, this is a function. Now let's try this other one. And that was f of x equals x squared. Let's try this one. If I run this vertical line and I pass it through here, oops, see right here, I've passed through 2 points at the same time. So because of that, this is not a function. So that's how you use the vertical line test. Super easy to do that. So what if you've decided that it's a function and now you want to know if it's one-to-one? So this is the same example. Let me make my line again. So here's my line. So just to verify that this is a function, so we know this is a function because it passes the vertical line test. As a matter of fact, let me show you over here. This is also a function because it passes the vertical line test. So both of these are functions. But what if you want to know if it's a one-to-one function? So is this one-to-one? Well, remember to do a one-to-one function, the y values can't repeat. And there's an easy way to test that as well. So if I take my line and I turn it into a horizontal line instead, and I'm going to run it up, I usually start at the bottom. And so I'm going to move up this way and I'm going to see if it passes through 2 points at once. It does right here. So because it passes through 2 points, we would say this is not one-to-one. It is a function, but it's not one-to-one. So let's try the other one. If I move it over here and I move up and I'm looking to see if I can pass through 2 points and I don't. So this is a one-to-one function. Now remember, both of them are functions. So f of x equals x squared is a function. It's just not one-to-one. It passes the vertical line test, but it does not pass the horizontal line test. My g of x equals x cubed is both a function and it's one-to-one because it passed the vertical line test and it passed the horizontal line test. Sometimes you can have a relation represented as a table. And so here the question is, determine if the relation represented in the table represents y as a function of x. So we're being asked, is this a function? So when we want to check this, remember what we're looking for. The x values can't repeat. So if I take a look at my table and I see I have a 1, a 3, a -1, a 2, and a 0. So since the x's don't repeat, it's a function. So now I check the y values. So I have a 3, 11, oops, I have another 3. So it's not one-to-one. And I'm going to give a reason. Since we have repeated y values. Okay, so that's how you do it in a table. Now, again, if you were graphing this, even if the dots lined up, and I don't know if they do, but even if the points lined up, you wouldn't connect them. Because if you're just given a table, then those are the ordered pairs that you would plot. Function notation is useful to describe a relationship between two variables. For example, we can describe the relationship between the height of a rocket as a function of time since liftoff. So notice the notation. Instead of using f of x is like the generic. So when you talk about f of x, that's like the generic function. F stands for function, a function of x. So h of t makes sense if you want to express the height as a function of time. When you change the time, it changes the height. Or perhaps the profit earned from selling a number of items. So the n represents the number of items, and the profit is a function of the number of items sold. So that is a good way to name functions when you're doing word problems, is to actually have them be make sense for the problem. So just like we often use x and y as generic variables, this is what I was just talking about, we often use x and f of x as generic variables in function notation. So here, if you're given that f of x equals 3x minus 2, and you're asked to find f of -1, that's like saying, take this number and plug it in where you see the x. So -1 is the input value. So we're going to take that and do 3 times -1 minus 2, which gives me -3 minus 2, which is -5. So I would plug in, I would get a -5 for my answer. F of 2 is telling me to take a 2 and replace the x with a 2. So I would get 3 times 2 minus 2. 6 minus 2 is 4. And then this last one, or part C, says to find f of m plus 2. Well, that looks a little different, but think about what we did in each of these cases. F of -1, I replaced the x with a -1. F of 2, I replaced the x with a 2. F of m plus 2, I'm going to replace the x with an m plus 2. And I still have the minus 2 at the end. So I'm going to have to distribute the 3. I get 3m plus 6 minus 2. So I get 3m, combining like terms gives me 3m plus 4. And that would be my answer. So you can even substitute other variables into the function. Now notice on part D it's different. So they're asking me, instead of, look where the x is. So this is like saying, okay, if they're asking me f of -1, then x is the -1 value. The -1 is the x value. But now the -1 is the y value. So this is different. So in this case, I take f of x, which is 3x minus 2, and I set it equal to -1, sorry. So I'm going to add 2 to both sides and divide by 3. So if I'm asked to solve f of x equals -1, think of it as like solving, they're telling me the y value is -1. I have to find the x value. I have to figure out what's the input value. And this is how you do it. You take your function, set it equal to that number, and then you're going to solve that. You can also find function values from a graph. So suppose you were asked to evaluate f of -2. So this is saying if x is -2, what's y? So think of it that way. So if x is -2, what's y? So you come to your graph and you find the -2. So here's my -2. So then I'm going to come up here on my graph and see what's the y value. Well, the y value looks like it would be 2. So f of -2 equals 2. On the next problem, I'm asked to find f of 4. So they're saying if x is 4, what's y? So I'm going to come over here and find the 4. And then I have to come up to my graph. Oh, it's not exactly right on a grid mark, but it looks like it's about 1.5. So I'm going to say 1.5. And this last one says solve for f of x equals 0. So now they're saying if y equals 0, what's x? So now I'm going the other direction. So if y is 0, so I have to find where is y 0? Well, y is 0 when it's on the x-axis. So right here, y is 0. What's x? 1, 2, 3, 4, 5. So the answer would be x equals 5. So when y is 0, the x value, you can kind of count that over and see that it would be 5. So here's another example. Let d of t be the number of ducks in a lake t years after 2002. Explain the meaning of each statement. So if t represents the years, then this would mean 5 years after 2002. So 5 years after 2002, d of t represents the number of ducks. There were 30, because that's d of t, ducks. So identify that the t is the 5 and the d of t is the 30. So 5 years after 2002, which would be 2007, there were 30 ducks. This would say this is the time. So 10 years after 2002, there were 40 ducks. So it's important to be able to interpret function notation and know what that means. You could also say in 2012. So I think that is the last one. So that's, kind of gives you a lot of examples for functions.